Hello friends, welcome back to my YouTube channel Chembiasis. So in this lecture I am going to discuss about the relationship between the acid strength and structure of different organic molecules. So in my previous chapter I have discussed about how we could measure the acid strength or pKa value of different acids and how the pKa value differs for different acids. So now in this lecture I am going to discuss about what is the reason behind different acid has different acid strength. So the direct relationship between the structure of the acid and its acid strength will be discussed in this chapter. So as you can see, we can see the pKa value of some of the acid right from hydrofluoric acid to hydrogen iodide. So if you see the pKa value as we are going from HF to HI, the pKa value drastically reduces. So in my previous lecture I have discussed that the lower the pKa value, higher is the acidity. So if you want to know why it is so, you can go back to my previous lecture where you can understood what is the relationship between the pKa value and the acid strength. So coming back to this lecture, as you can see, as we are going from hydrofluoric acid to hydrogen iodide, the pKa value decreases, so the acid strength increases from hydrogen fluoride to hydrogen iodide. Now what is the reason behind this? So as you can see that we are going from hydrogen fluoride to hydrogen iodide, the main difference is the halide ion. So as we are going from HF to HI, the size of the halide ion is increases. So we are going from fluorine to chlorine to bromine to iodide or iodine. So as the size of the halide ion increases, the size of their orbital will also increase. So because of that reason, there is a mismatch or the mismatch in the overlap of hydrogen s orbital and the orbital of this halide ion. Because the hydrogen s orbital is small in size, but as we are going from fluorine to iodide, the size of the orbital of the halide ion increases. So because of that mismatch in the size of 1s orbital of hydrogen and the other orbital of this halide ion, due to that mismatch the bond become weaker. As we are going from hydrofluoric acid to hydrogen iodide, due to the difference in the size of the orbital, there is a less overlap between them, and that's why as we are going from hydrogen fluoride to hydrogen iodide, the bond become weaker and weaker. So as the bond become weaker, it is very easy to break the bond and produce the proton. So that's why as we are going from hydrogen fluoride to hydrogen iodide, it is very easy to produce the H plus as the size of the halide, corresponding halide increases. So that's why as we are moving down from HF to HI, the acid strength increases, and that's why the pKa value decreases. So the relationship between the structure and acid strength, now I hope that you could relate. Now coming back to this example, so as we are going from this molecule, that is methane, to ammonia, to water molecule, to hydrogen fluoride, as we are going from methane to hydrogen fluoride, the pKa value decreases, which automatically suggests that as we are going from left to right, the acid strength obviously increases. So if you see what is the difference between these molecules, the common thing is that hydrogen, and the difference is that as we are moving from left to right, we are going to carbon, from nitrogen, from oxygen to fluorine. So as we are moving from left to right, the electronegativity of the corresponding atom increases. So we are moving from carbon to fluorine. So as the electronegativity of this atom increases, the polarity of that corresponding bond, here in case of CH bond, in this case NH bond, in this case OH bond. So as we are moving left to right, the polarity of the bond increases. So as the polarity of the bond increases, there will be more partial positive charge on hydrogen atom. So as we know that if we have A and B, AB, this is the molecule, and if A and B has severe difference in electronegativity, then there will be partial positive charge on one atom and partial negative charge on another atom. So that's why, and as the polarity increases, the amount of that, or the effective partial charge on each atom increases. So due to that reason, with increasing the electronegativity, the stability of the conjugate base increases. So suppose this carbon atom, okay, so as we have discussed that if an acid is a very strong acid, then their corresponding conjugate base will be much more stable. So the stability of the conjugate base also decides the strength of an acid. Now in case of methane, this molecule, when it loses one proton, it becomes CH3 minus. So this CH3 minus is the conjugate base of the corresponding acid methane, if we consider methane as an acid. On the other hand, if we see hydrogen fluoride, if it loses one hydrogen, it forms fluoride minus. This is the conjugate base of the corresponding acid hydrogen fluoride. Now if you see the difference, you can easily say that okay, fluoride minus ion will be much more stable than this methide. This is because the fluorine has very high electronegativity, so that's why the electron that is residing on this fluorine atom will be much more lower in energy. On the other hand, the electrons that is reside on this carbon orbital are having much higher energy. So that's why this methide ion is much more unstable compared to fluoride ion. So the stability of the conjugate base, in this case if you compare the stability of the conjugate base, fluoride ion is much more stable. So that's why hydrofluoric acid is having much more higher acidity than methane. The same order is also followed as we are going from carbon to nitrogen to oxygen to fluorine. Okay, so you can see this is the order of the stability of their conjugate ion or the conjugate base, and the order of the acidity will be its reverse. Okay, so if you consider CH3 minus or NH2 minus, these are extremely strong base because of their conjugate acid is extremely weak. So overall, if you see, if we are going from methane to hydrofluoric acid, as we are going from carbon to fluorine, so left to right side of the periodic table, acidity increases. The increase of the acidity is because of the stability of their conjugate base, due to, as we are going from left to right, the electronegativity of the atom, that is carbon to fluorine, increases. On the other hand, if we go move from down up to down in the periodic table, as we are going from water molecule to this molecule, the size increases. Due to the increase of the size, there will be mismatch in the overlap, and that's why the SH or the ACH bond will be much more weaker compared to this OH bond due to the mismatch in their size, and that's why it is having very high acidity compared to water molecule. So as we are moving from up to down, the acidity increases, and as we are moving from left to right also, the acidity also increases. Now I will discuss what is the effect of hybridization on acidity. So let's try to understand this with some example. So this is a molecule that is called acetylene. It has pK value of 25. On the other hand, this is a molecule that is called ethylene, which is having a pK of 44, and this is a molecule that is called ethane, which is having pK of 50. So as we can see, if we compare the acid strength, the acidity decreases as we are going from acetylene to ethane. So what is the reason behind this? So to understand this, let's try to understand the stability of electron. So for any atom, we know that at the center of the atom there is a nucleus which is positively charged, and initially there is a s orbital, and after that there is a p orbital. So if we see the shape of the s orbital and the p orbital, s orbital is spherically symmetrical. On the other hand, the p orbital has two lobes. So if we see the shape of the s orbital, the electrons that is residing in the s orbitals are residing much closer to the nucleus because of its shape. On the other hand, in p orbital there are two lobes that is outwards getting away from the nucleus. So that's why the electrons that is residing in two p orbitals are residing much higher distance from the nucleus than the electron that is residing in an s orbital. So that's why the electron that is residing in 2p orbitals are having much more higher energy than the electrons that is residing in 2s orbitals. Okay, so the electrons that is having residing in 2s orbital is much more stable in energy. Now let's try to see the hybridization, effect of hybridization. Now if you see the molecule acetylene where carbon is sp hybridized. So sp hybridized mean it has 50% s character, the carbon atom. Okay. On the other hand, if you see the molecule ethylene, it is sp2 hybridized. So the s character is 33.33%. On the other hand, if we see the ethane molecule, it is sp3, the carbon atom is sp3 hybridized, so it has 25% s character. So as we are going from acetylene to this molecule ethane, the s character decreases from 50% to 25%. So this carbon atom and the orbital of this carbon atom has much more higher s character, and that's why the electrons that is residing in these orbitals will be much more stable in energy. Okay, now let's try to see what are the conjugate base that is produced of this acid. Now we will see that the conjugate base of acetylene is this ion. Okay, so here the electron is residing in sp hybridized orbital where 50% s character is there. So that's why the electron that is residing in this sp orbital is much more lower in energy. So that's why the stability of this conjugate base is much higher. On the other hand, if we see this molecule, the electron is residing on sp3 hybridized orbital, which is having only 25% of s character. So that's why the electron that is residing in sp3 hybridized orbital is having much higher energy compared to any electron that is residing in sp hybridized orbital. So that's why this ion is much less stable compared to this ion. So this is the order of the stability of the conjugate base. Okay, so the order of the acidity will be reverse of it. So this is the acidity order. Okay, so we have told that the more stable the conjugate base is, the acidity will be more higher. Okay, so this is the acidity order. Now I will discuss about what is the effect of inductive effect on acidity. So if we see the molecule ethane, it has no inductive effect. On the other hand, if we replace the hydrogen atom with a fluorine atom, then we will see that the fluorine atom will draw more electrons towards it, because fluorine atom is much more electronegative compared to carbon atom, and because of that electron inductive effect, there will be partial negative charge will be created on fluorine atom, and some partial positive charge will be created on these two carbon atom. So this inductive effect is a type of electronic effect that is propagating through the bonds. Okay, so as you can see that the inductive effect is propagating through the bond, and this inductive effect is depending upon the difference in the electronegativity as well as the distance between the two atoms. So you can see that carbon C1 atom is much more closer to the fluorine atom, so that's why the inductive effect produced by the fluorine atom is much more higher on carbon atom. So that's why the partial positive charge that is produced on C1 carbon atom will be higher than the C2 carbon atom. Okay, so so you can see that the inductive effect decreases as the distance from the atom decreases. So if you want to understand about the inductive effect more, I can give another lecture on inductive effect. So that's it from this lecture series, and I hope that you like this video, and if you do like this video, don't forget to subscribe to my YouTube channel Chembiosis. And if you do have any questions or queries regarding this lecture, you can ask me through the comment section. So that's it from it, and see you in the next lecture. Thank you.